I will talk about the Turkana Jet and rainfall in CMIP 6. I am Oscar Lino. So we are focusing on East Africa, which is a dry region in otherwise a wet equatorial belt. And the region is exposed to climate extremes such as drought and flood. So these disasters have increased them in their manifestation in the recent past, being about the need and use for climate information for models. The TJ is an important factor to rainfall, especially in northern Kenya. This one has been known through use of model data. So by the way, different models simulate the TJ differently. But reasons for this has been documented, and that's what we need to, what we're trying to document through this work. So we are guided by these research questions. What are these features of the TJ in different models? How might resolution and representative topography in the models be related to this? Tying up that with rainfall. We are doing climatological analysis between this period on wind speed, omega and precipitation, as well as surface pressure from ERA 5 and CMIP 6, focusing on 26 models which have the variables which we need for this analysis. We'll do the analysis on native grid for the models just to preserve the regional information. So we'll show the seasonal cycle of wind vectors at 850. We'll show vertical profiles of winds along Turkana Channel. We'll have some thresholds for the TJ, as well as index for the shape of the Turkana Channel, and an index for precipitation, just to be able to analyze variabilities in the Turkana Jet. So what we see here is the seasonal cycle, saying that we have this splitting of flow to form the TJ and the Somali Jet, well seen in ERA 5 and the Hadjem, but not in the BCC model. When you picking a point within the Turkana channel, you see that values in ERA 5 and Hadjem are more comparable all through the year. The range of values in ERA 5 are between 11 and 13. Similar range of values in the Hadjem between 8 and 10, but the values are more varied in the BCC model, and they are particularly low during presence of the Somali Jet. We also see that moisture, in terms of moisture transport, we have relatively low moisture being transported in the BCC model. So profiles of wind speeds, we see center of activities during GJAS when we have the Somali Jet present closer to the entrance area of the Turkana channel in these different models. Apart from the Hadjem and ERA 5, as well as the two versions of the CNRM, where high wind speeds tend to reach mid Turkana channel area. But when that is absent, we see that there's acceleration of wind speed. Of winds at mid Turkana channel, and here we see that the core is the mid of Turkana channel area. Here we have the shears a little weakened, and these different models, but they have a vertical elongation. We have the core values a bit being observed to more higher levels. So in omega, we see that there is subsidence just above the core area. During this period, we have the core closer to the entrance area, and that's where we have high subsidence motions. Apart from the CNRM, which equally shows a strong subsidence closer to the core. I remember that that there was equally high wind speeds at core area during this period in the CNRM and the ERA 5 model. So when we in the other months of the year, when the core is more shifted towards the center, we see that we equally have strong subsidence closer to the mid Turkana channel. So we also have ascents emanating from near entrance of Turkana channel where the surface elevation begins peaking. But once that is sloping downwards again, we see that that generation of ascents is vanishing. So this one plays an important role to enhancing ascents at the exit area of the Turkana channel. So during this period, which is this season, we'll tie up that with rainfall. So just to understand further how and why you are seeing ascents from closer to mid, and I mean from within the Turkana channel. This is the Turkana channel in different models. Values, and I mean the surface elevation for at least for below 900 hectopascals, which have been masked out. So we've attempted to estimate the cross-section areas as you cross from the entrance to exit the Turkana channel. And that's what we see in this figure, that there is narrowing and towards a formation of a constriction at 37 degree east. There is consistency in how that is changing in ERA 5 and the Hadjian model. The Canadian has very high changes in the cross-sectional area, but there is discontinuities in how the cross-sectional area changes in these other models. So just giving a mean for that, we have an index for the Turkana channel in these different models, which is very high in ERA 5 and the relatively high resolution models. But differences begin once the resolution is slightly greater than 1.5 degrees. So again, this is tying up the index with the strength and the strength of the TJ, and what we see is that at a very loose criteria of considering maximum wind speeds of at least 6 and shears of 2, most models return a Turkana Jet count, but that one begins rapidly changing beyond 9 meters per second and 5 meters per second shears. We see that beyond that, the number of models that return a jet count are decreasing. So again, we want to see how if fluctuations in the TJ affects rainfall, and we see that when the TJ is strong, we have dry and anomalies at the exit in areas where rainfall is during JJAS season. So this is basically advection of dry winds bringing about that kind of dry anomalies. And when the jet is weaker, we have wet anomalies due to enhancement of the vertical ascents. So at a more stricter criteria, we see that these models which have a jet at very strict criteria are actually models which have a fairly good TJ structure in them, and they transport more moisture. So when the jet is stronger, then there is basically an advection of moisture from the exit area further to the west of South Sudan. Just summary, tying up everything is that this TJ is important to northern Kenya and northwestern parts of East Africa, bringing about enhancement of rainfall. So the TJ is a bit irregular in these models, and during presence of the Somali jet, the wind speeds decelerate. There is conflation of the TJ and the Somali jet. In absence of the Somali jet, which is also the East African level jet, the winds are allowed to accelerate through the channel, and the core is elevated, and that one weakens wind shears. So we have ascents emanating from discontinuities from narrowing along the Turkana channel in the models, and that blocks low-level wind flow and impulse deceleration. So we have a common jet in these different models characterized by 9 meters per second maximum wind speed and shears of 5 meters per second, and fluctuations up and above that causes also anomalies in rainfall of up to 8% of the climatological rainfall. So just to conclude is that we have this work agrees with several other relevant work on the TJ, but additionally we know that we've seen that the TJ is irregular in 6. We have these thresholds for the TJ, which are a bit lower than those ones conventionally used in the analysis, using reanalysis data sets. However, that one is an aspect of narrowing in the Turkana channel that is important to maintain the TJ being deformed by resolving topography at this kind of resolutions. So, however, we've not answered everything through this work. What's still unknown is that we've seen that we have a perennially weak TJ being forced to a stronger TJ and vice versa. But that one is not known. So we still recommend that we need further, again, field studies to ascertain associations between the TJ and rainfall. Thank you.